So it's a pleasure for me to be here today to talk to you a little bit about my passion. And my research area can be aptly entitled as Cyber-Physical Security of the Smart Grid. We hear a lot about cybersecurity issues, but cybersecurity is morphing into a more general form of security that I'd like to discuss today. So one of the interesting things is I had recently an identity crisis because, as was mentioned, I'm chair of currently electrical and computer engineering, but I'm also a researcher. And as chair, you really talk about this need to build community. This is a very important thing to have in a department. But as a researcher, I was essentially saying, please trust no one, okay? So as a chair, let's all be friends and get along and be inclusive and then be very, very careful in my research. I was also saying that it's important as an educator. It doesn't work. I don't think it does, but I will try. I'll keep trying. So I was saying that it's important to have breadth, and as you all know, our students really have strong technical skills. We're very lucky we get some of the top students, and it's great to prime them with leadership skills and very broad thinking. So as chair, we advocate for that. But as a researcher, I was saying, no, don't be broad. be very focused, because that essentially helps for security. And then as chair, in support of our wonderful current dean and our wonderful previous dean, we really want our students to just be ambitious and go for it and be fearless. But as a researcher, I was essentially saying, you need to be afraid. Be very, very afraid. So when someone has an identity crisis, it's always best to go back to first principles. And so, what are they for an engineer? And so if you go back to what we're trying to protect, why cybersecurity is such an issue today, and why it has such an impact, it's because we live in a world with instrumentation, interconnectedness, and intelligence. And what that essentially means is we're in this world, this ideal world of a smart city. And a smart city generally has critical infrastructure that support it. And my work involves, and I will argue that the power infrastructure, the energy infrastructure, is the very most critical, because other critical infrastructures like banking, telecommunications, transportation, agriculture are really built upon and depend on our power grid infrastructure. So as we are harnessing our instrumentation, interconnectedness, and intelligence for the power grid, it is becoming what we call the smart grid. Now, just to discuss what is a smart grid, it's a, you can think of it as an engineer in a very detail-oriented way. It's the integration of information technology with the power delivery system. But I like to think of it in terms of what distinguishes it from the classical grid. We have now two kinds of flows. We have information flow because it's intelligent, and we have energy flow. Okay, it has to serve the needs of people who need power. And so what the smart grid essentially does is make that bidirectional. Our classical grid, it was unidirectional. Information went from the home to the utility for billing, and power went from the utility to the home. But now you have people doing local generation at their home, and they can sell back energy to the grid, and you have information being sent to the consumer so they can make decisions as to when they want to use their appliances. So you see this bidirectional flow of information. Now, when you're looking at, securing something, okay, or even and trying to envision what the best way to design it is, initially, the descriptions of the smart grid, were very different depending on who you talk to, but it's best to look at what's common. And if you look at the definitions from the European Union to, for example, General Electric, two things stand out as to what makes this smart grid unique. And one is that it's open, and the second is that it's consumer-centric. Okay? Open in the sense that everyone should be able to participate. You're looking at a deregulated situation, deregulation, and you want to be able to more aptly meet the consumer needs. And this is why we need information. This is why we need to merge information technology with the power grid. And so this requires information about the right thing to the right party at the right time. And so this is termed cyber enablement. And so once you start to have cyber infrastructure in a system, you have to be aware of cybersecurity issues. And so the one nice thing is this is not the first system we've ever had to cyber secure. This is not the first sector that has been cyber enabled. We can always draw upon what we've learned in the past and what history has essentially taught us. So commerce has become e-commerce. For example, we've seen paramount changes in banking. Entertainment is now digital entertainment, and even social networking has changed friendship. So there's been a cyber enablement in a variety of sectors. And so what we've seen is in all of these cases, cybersecurity has been an issue. For example, in commerce, impersonation is an issue, entertainment, piracy, and in social media, privacy for sure. So what we've learned essentially from those systems is that cybersecurity should be part of the system design. Cybersecurity is a support service that should not hinder usability. What this means is cybersecurity should still facilitate easy operation of the system. It shouldn't come in the way. If it comes in the way, people try to find ways to circumvent it. And you want people to embrace security. And cybersecurity is also a process. You can't buy one patch, you can't buy one piece of software that will protect you indefinitely. It's something that has to be managed and maintained over time. But there are distinguishing characteristics if we look at the smart grid. If we just look at where we are in terms of the times, currently, cybersecurity is considered to be a foundation of the digital economy. And this is a big deal because having been a cybersecurity researcher for 25, 30 years, often you really had to make a case. People didn't think it was an issue. But now it is considered to be an ingrained part of any IT system. It protects business value. It drives digital agility, meaning people are much more likely to be more innovative, and it enables innovation and growth more generally. So another distinguishing feature is if we look at the kind of attacks we see on industrial control systems and energy infrastructure, they're very different than what you'd see on these other kinds of systems. Energy infrastructure is a big target because there can be a profound impact on a society if it is affected. And so we're starting to see attacks that are very intelligent. First, they're patient. What we can say is stealthy. And they are polymorphic. So if you look at three of the most well-known types of malware on industrial control systems, Stuxnet, Black Energy, and Havex, from the time they were deployed and initially infected a system, it's typically years until they're detected. And what's happening within those years is they're slowly propagating into the system, gaining information about how it's set up, what typical behaviors are of users, the overall architecture of how devices are connected, and they're sending back that information. Okay? So there's a great deal of patience on the part of individuals who are infiltrating these systems. And then when the attack starts, they're typically detected. So they're very stealthy and they're difficult to detect. And also you're starting to see they're polymorphic, meaning they change how they behave. So they're very difficult to track. The other distinguishing feature is what we call the cyber-physical interface. In the other applications I talked about, entertainment, friendship, commerce, the cyber-physical interface was typically a human with a computer. With the grid, it's actually very different. The physical aspect isn't a human, it's our energy, it's our power grid infrastructure, and it's a very distributed system. So the high-tech information technology is integrated into the power grid in a very distributed way. It's complex, it's a highly connected system, and it's collaborative. So this is beautiful because all of these things give you these bells and whistles and make the smart grid promising and consumer-centric. But the problem is when you look at these three things, complexity usually means when things are complex, it's much more likely to make mistakes. You may have aspects of the system that you are unsure about, that you are not clear in terms of its operation. Just because it's too complicated, it becomes more unpredictable. So you have flaws. When things are more connected, okay, so they're connected, physically connected, of course, but also connected in terms of communication networks, you start to have access, remote access to the flaws. And when you start to have collaboration, what that means when you have an engineering system, you're collaborating, you have to be able to provide different entities the ability to affect one another. When different parts of a system can influence and affect one another, you then have the ability to exploit a weakness. So the intersection of those three things, flaw, access to the flaw, and the ability to exploit the flaw, is by definition a vulnerability in cybersecurity. So what's beautiful about these characteristics makes it what it is, but it also leads to these vulnerabilities that we have to be very careful of. Now, vulnerabilities are very different in these newer systems, as we're seeing, these cyber-physical systems. So they're not purely cyber systems. There's a physical element because the cyber is intertwined within the physical element, here being the power delivery system. And so there is, within these systems, a very tight coordination of things. And so this leads really to a rich environment to do research and to find ways in which to protect it. So when we look at security, we really have to look at two things. Not just protecting it and preventing attacks, but attacks are a natural part of life. It happens all the time. There's attempts, you can block them, but sometimes you can't block them. So we need to be able to detect them and react to them. And so resilience is the other issue that we look at today. So we typically look at both security and resilience is becoming a fundamental part of security today. So I thought we'd talk a little bit about security. And I know this being a lunch and learn, many of you have a technical background, so it's wonderful for me to talk to you about this. And I'll just flash a few mathematical equations in case you're curious how things look. But I will focus on giving you an intuitive understanding of things. Okay? I'm very proud of our math. So when we look at cybersecurity, it's a very abstract thing. A lot of people don't know what that means. So essentially, there are different, in a cybersecurity securing situation, you need to figure out what your attacks are. What are you protecting? What is the target? And what are you protecting against? So when you look at any system and you're trying to secure it, you need to identify for yourself what is the asset you're trying to protect. And you, within a power grid, there's many assets, and you have to do this exercise for every asset. And there's physical assets and cyber assets. So you look at the asset, you try and determine what the vulnerabilities are of the asset. And vulnerabilities are a fact of life. You will have a vulnerability. Often you can't go around it because you need the system to operate well. Okay? By nature, there's a tension between having innovation and having vulnerabilities. So you will have a vulnerability, but that doesn't mean you will be successfully attacked. You have to protect that vulnerability. So you identify the vulnerability, then you try and figure out what the threat would be. A threat is a potential. Okay? What potential exists? Who would want to exploit that attack? And then if an attack would take place, what it would look like and what the consequences would be. And basically your job is to try to create a countermeasure, and that's the middle block there. Okay? You just block the attack, and you have active attacks that make changes to the system and passive attacks that just are there for reconnaissance. They're eavesdropping, simply, very quietly. So what do attacks look like? In the area of cybersecurity, we basically list them as these four possibilities. So 99.999% of all attacks, when you talk about cybersecurity, are any one of these four or a combination of them. Okay, so you can intercept, just eavesdrop. Okay, you can modify, you can interrupt, block, and you can fabricate. Okay, so you often look at any combination of those, and there are well-known ways, tools, primitives, so basically cryptographic primitives that can help protect against those. So we have encryption, digital signatures, authentication. With respect to someone blocking or jamming something, there's nothing you can do. You just have to try to detect it and find other means to communicate. So there's a response that's required there. So when engineers look at cyber securing something, there's typical best practices. And this is what they look like for power grid infrastructures and general IT systems. Okay? You have to model the threat, you have to segment. Okay? Separating the system is key. Often your best defense is isolate yourself. Okay? Isolate the components. If you will often see in a complex system, a cyber attack starts, it starts to propagate in the system, just cut yourself off. Okay? So you create a gap between yourself and the attack. There's honeypots, which is kind of nice. So you put on the network an innocent looking computer and you want someone to attack you, so you model what the attacker's like. Okay? So you gain some information. And there's a variety of other, just reviewing the source code. So there's a variety of principles. Also, there's governance. Okay? The energy grid being a critical infrastructure, we in North America rely on the North American Electric Reliability Corporation. It used to be a council. It became a corporation after the 2003 Northeast blackout. When it was a council, it was a voluntary group whereby power utilities shared information about what made them more reliable. But after that blackout, it was realized that we needed something to be mandated. Okay? So it became a corporation, and so what that group does is if they have a set of standards, some of those standards include cybersecurity standards, and if a utility is not practicing those principles, they can get fined up to $1 million per day. Okay? So there's a great deal of motivation, and this is what the standards essentially look like. They're called the CIP standards. CIP is an acronym for Critical Infrastructure Protection. And so this is what the standards look like, and the pink ones are for physical, because, and the blue ones are for cyber. And the reason they're both there is they are intertwined. Oftentimes, if you ask very successful hackers how they were able to infiltrate a system electronically, they often first physically went into the building, impersonating a system administrator, and pretended to be someone trustworthy and got someone's password initially. Okay? So the two go hand in hand. You need both physical security and cybersecurity, especially for critical infrastructure. Another interesting thing is that we're seeing a shift in what's important in terms of cybersecurity. So if you talk about the general pillars of cybersecurity, what does it mean to secure something? There's 3 elements. Confidentiality, so making sure that the information is basically private. So assets are accessible only to authorized parties. So if you were doing banking, you don't really want anyone else to be able to read your communication. So you need confidentiality. Integrity, you need to make sure the information is truly what it says it is, and it's from the authorized party. And availability, you need services to flow. You need access to information. And typically in standard IT, the most important was confidentiality, then integrity, and then availability. But what happens when you're looking at critical infrastructure is it's almost flipped. Okay, so it's a very different mindset when you look at IT. Availability is the most important thing, because in critical infrastructure, the information system is a secondary system, and the objective of that secondary IT system is merely to support the critical infrastructure operation, in this case, the power flow. So you want to make sure the power grid is operational. You only care the information is protected, private, it has integrity, in as much as it helps you get the grid functional. So accessibility, availability is number 1, then integrity, and then confidentiality, okay, in terms of priority. So, so that kind of gives you a brief glimpse of what cybersecurity looks at, and I'll give you an example of a real grid situation, but let's next talk about resilience. And this is where a lot of the research is at right now, looking at resilience, because cybersecurity has been addressed for decades now, and so it's a matter right now of fine-tuning that. But resilience is something where there's a rich open field of study. So what resilience essentially is the ability to bounce back from a disturbance, and it's the capacity to adapt to changing conditions. And so we need resilience, and interestingly, when I draw on the parallel as an educator, we would love to build resilience in our students. As an engineer, a cybersecurity engineer, we'd love to build it within our technical infrastructure as well. So resilience is the prevention, minimization, and recovery from adverse consequences. Okay, so it's multidimensional, and so I like to provide this visual. to discuss what it means. So this is a very complex system, the grid. But you know, and there's many ways, many parameters to change, many ways to get that grid to essentially be stable. And what the objective, you think of it in a very simple way, of the power grid is to balance energy production with energy demand. Okay? Because oftentimes you don't have anywhere to store the energy, it has to flow. Okay? So you need the two to balance. You need energy production, generation, and load to be balanced. So the system is very complex to achieve that balance. There's many parameters, many things you can change, and many ways in which to balance it, and many physical parameters to look at. But essentially, you want the system to be robust, and more resilient. So there's different metrics we can look at: latitude, resistance, and precariousness. And anytime we make a design change to the grid, we aim to improve on these. So anytime when you have any complex system, the power grid or otherwise, you have to be robust to disturbances. Okay, things will change. Okay, and if it's a small enough change, the system will recover and go back to operational state. But you can have a situation where if the disturbance is too great, it's unfortunately in a situation where it will no longer go back into a healthy state. So this is what you want to avoid. Resistance gives you that ability where the system pushes back because of momentum or some sort of inertia. So it resists a disturbance, so it will remain operational. Latitude gives you a metric in terms of how much it can be changed before it will no longer go back to an operational state. And precariousness is, okay, how close are you to that limit? Okay, so in a power grid, if it's stretched to its limit, meaning demand is very, very high, it is more sensitive. That margin to instability is greater. And so the resilience best practices are basically be listed as follows. You need some sort of adaptation. Okay, the system's got to at least bend a little bit to a disturbance. If it's too rigid, it'll break. You need to monitor. You need situational awareness. So that IT element is very important. As always with any system, I'm sure everyone in this room can agree, you need redundancy, parallelism, and hierarchy. Hierarchy is something where when you have a very large-scale system, it allows you to be able to make it more scalable in terms of design and management. And distributed control. Whatever we do, whatever control we try to do to change the system, it's best if it's distributed in terms of centralized. So the overall goal for resilience is, say we start with the blue system, and so if we look at this as a visual analogy, if you can see, if we look at that colored, the white ball, a disturbance will push it out of that well, and if it pushes too far out, past that threshold, it will fall and no longer be in the valley. You want to make changes to the system and have the system react so that it becomes the pink. Okay, so the well is deeper, it's harder for that ball to get out of the well, and it needs to be pushed much farther before it actually leaves the well. Okay, so that's the spirit, the intuition. So the R&D questions we look at is, what are the vulnerabilities that we have to deal with? And it's not simply the cyber vulnerabilities. We know those pretty well. It's not even just the physical vulnerabilities. The industry knows that. But when you couple the two, you have new vulnerabilities. What are those new vulnerabilities? How can we add security and resilience to the system, and how do we prioritize it? Because this is a really monumental task to secure the grid. Where do we start, and where do we get the biggest bang for investment? So my research group currently looks at a number of different things, and I thought I would just kind of give you a flavor of 3 of them. Okay? And I'll just flash a little bit of math, just so to remind you of your school days. But I'll also provide you with some intuition. Okay, so we do all of this modeling, all of this fun stuff, all these simulations, because we often try to see what attacks are possible when IT infrastructure comes and integrates with the power grid. Okay, and what the goal and the objective of the attacker, and you have to think like the attacker when you do research in the area, is really to have a cascading failure situation. So ideally, this is what the attacker would like to do: start a fire and have it just keep going. What we want to do in terms of protecting the grid is it will start somewhere small, and then it will propagate, And as I mentioned, if you saw the slide where, you know, it takes 2 years before it's detected, it will sit there for a while patiently, trying to figure out at what point it can have maximum impact in multiple dimensions in the system. We would ideally like to prevent the propagation of that cascading failure. So we want to design systems where there's a natural barrier, okay? And being engineers, we would like to create also a scenario where we reinforce the physical system with information technology in a very effective way. Okay? So if we reinforce the physical system, if both the cyber and the physical work together, we have a much more resilient system. So those are the 3 ways of thinking we have in the research. And in terms of, you know, the tools we use, if we get down and dirty, we have a cyber system and we have a physical system. And this is a beautiful modeling problem, because how do we model the physical world? Well, physics, and we make use of ordinary differential equations. Okay? So we have that continuous time ODE models, and that's very important when you're looking at a physical system such as the power grid, and there's decades of modeling knowledge in the power industry. But we also have this cyber system. Cyber system is digital, it's discrete, it's logical. So we use graphs. And graphs are a very convenient way, a compact way to represent pairwise relationships. So in the work we do, modeling is very important because we're trying to look at how the system behaves to attacks, what we can do to make it more resilient. And so we essentially look at different models that merge these 2 tools. Okay? And there's different ways of merging these. And I'll give you some examples. So let's start with you know, vulnerability analysis. Let's talk about the creation of an attack. So we're going to, what's of interest really to the energy utility industry is fabrication, because if you're looking at operations, okay, there's different information systems from, for example, smart metering in the homes. We're not looking at that. We're looking at operational technology information. So fabrication of sensor data is a very difficult thing because it can get the system to make decisions that are actually not in the best interests of maintaining stability. And we want to make sure the information is available because the power grid depends on information to operate. We want to make sure there's no interruption. So we typically look at attacks of this sort in the system. And we've been looking at many kinds of targets. So I'll talk to you about one. We've done studies to look at when the target is a physical piece of equipment, it's a synchronous generator. Okay? And so this is important because this represents the majority of you know, production of the commercial electricity industry, and it essentially looks to convert mechanical power to electrical, and it's very well modeled. And so let's look at a very simple system and to give you an intuitive flavor of what it looks like. So say we have a 3-generator system. You see the circles, 1, 2, and 3? They're all synchronous generators. They're attached through transmission lines. You have loads. This is what it looks like. So essentially, we can model it mathematically. Okay, so those are ordinary differential equations. There's a sine function, scary. Scary means it's nonlinear. And so you know, there's 3 generators, and we look at it from the perspective of the generator. We need to, that's the target. And so they're all coupled because they're physically connected. And so we can model everything mathematically. And essentially, what can an attacker do? So with the smart grid, the way classically a power grid regulated itself in one way was to reconfigure itself with circuit breakers opening and closing. So certain things were connected and then they were no longer connected, and that managed the balance and the flow. Okay? So if a tree fell on a transmission line, it would be detected and automatically the breakers on either side of the transmission line would open, and so then the system would rebalance. So an attacker can make use of that reconfiguration. Now that reconfiguration can be done remotely because these circuit breakers are connected to communication networks, an attacker can open and close breakers, okay, newer ones. So you have a situation where you have this dynamical system that can now change its dynamics. You can have an attacker go in and start changing its configuration. And you can do it in a certain way where the system basically can switch, okay, different aspects on and off. And within the literature of control, specifically variable structure systems theory, if you switch between dynamics, you can actually get a runaway situation. You can switch in a way that's intelligent and it keeps the system stable. That's usually how the control community uses it. But an attacker can use it to make it go unstable. So this is a visual where the red shows you have two systems, two dynamics, two switch configurations, blue and green. And if you switch in a certain pattern, you can create the red scenario. You switch in one pattern, it's stable. You switch in another pattern, you have a runaway and unstable situation. So you can have a situation where, say you have, for example, let's look at this small system here. This is modeled, this is called the New England 10 machine 39 bus system. It's a well-known system, modeled after some aspects of the New England system. And you have 10 generators here. And so say that's the target. Okay? And you have a certain rule. There's a mathematical rule to how you open and close the breakers. You use that, and those are the breakers that you open and close. And so you can bring that down, and then the focus of the attacker becomes, instead of generator 9 before, now generator 8, and they use those same breakers, switch with a different rule, bring that down, and that starts the cascading failure of the system. So you can have the overall system come down, and then in a matter of seconds, and you have a very reduced system with just generator 10 working, and it's servicing very, very small resulting load. So this is how a cascading failure situation can essentially manifest. We can also look at how to protect against this. And we can go back to our beautiful mathematical model as well. And we can talk about how can cyber help. Okay? So that's how cyber can harm. How can it help? So what you can do is you can cyber reinforce things. You have these generators. If you give the generators sensors, if you give them a local storage device, and what energy storage device like a battery or a flywheel does is it absorbs energy and it gives it out. So it can be kind of slack, okay? And it can be effectively used to rebalance the system. So essentially you can cyber enable those generators. You have situational awareness, you have some sort of control, so you can take additional extra energy that you don't know what to do with, or you can produce energy when it's needed because you're trying to maintain balance. And you essentially can create a scenario where the dynamics changes. And as an engineer, what that means is you add this plus U. Okay? And if any of you remember your control courses, the plus U is nice. You have control over you. Okay? U in this case means you're dictating how the energy storage device absorbs and puts out energy. And so that U, what it can do is it rebalances the system. Okay? So this is an example of an energy storage device, a flywheel that could be used. So what that essentially means, that U, is you have this, these generators, but they're reinforced. In a power grid, you need those synchronous generators to be synchronized. Okay? They need to be operational in North America at 60 hertz. You don't want them deviating. Okay? So what happens is the physical infrastructure, it's designed so synchronization can be maintained. But if there's a disturbance or there's a cyber attack of some sort, that coupling starts to degrade, and then you can have a runaway situation or a rundown situation. You get instability. So you reinforce that with the cyber. Okay? So the cyber, the information helps actuate change and keeps the system more stable. And so this is essentially how we have more cyber physical coupling. And so I like to think in terms of an analogy, the kind of analogies we use is that of a flock of birds. If you look at the dynamics of the power grid, when we're trying to keep the generators synchronized and working together, okay, it's like a flock of birds, okay, where there's a strict analogy. A generator has two important states. Its frequency, a synchronous generator, and its rotor angle. This has an analogy to the velocity and the position of a flock mate in a flock of birds. So if the storage device can behave in a way so the dynamics mimics a stable flock of birds in the face of a disturbance, you can have a more resilient grid. So we're borrowing from nature in order to add resilience. So our dynamics have many mathematical components. There's goal seeking. A flock of birds do have a destination goal. Velocity matching. Each flock mate in a flock match their velocity so they can remain in formation. and flock centering. Okay, so they don't want to be on top of each other, but they want to be adjacent to each other. And this is necessary for the power grid. You need generators to all have the goal of being at 60 hertz. They need to match these speeds, and they need to have phase angles that are not exactly the same, but around the same value. And so if we can model our dynamics to be like a robust flock of birds, the idea here is we can have a better, more resilient grid. So if we look at the analogy with the flock of birds, so if you have a disturbance in the grid, if you consider each bird to be a generator, what will happen when you have some sort of cyber attack or disturbance is the system will naturally partition. Some generators will behave very similarly, and they'll cluster in groups. So if you have the analogy to the flock, that's what will happen. Okay? You can see that if you look at the generators and you look at their voltages and their currents, they tend to cluster and group together. That's bad for the grid. So what you essentially want to do is you want a scenario where the biggest generators in those clusters keep together, harnessed with cyber infrastructure and storage. And so you maintain stability in that way. Okay, so this is intuitively can be described as using the information system, the communication networks, to help intelligently use storage and provide a more resilient grid where cyber reinforces the physical. And last, I'll talk about some cutting edge stuff that we're doing with Hydro-Quebec in terms of what we call IT-OT convergence. And this is the big thing right now in the energy sector. So communication networks are merging. Okay, so why is that? Because it's nice if they're connected so we can have sharing of information in a central place to get global visibility. There's many kinds of networks in the power grid. There's the IT network that provides the business value, and then there's the operational network that actually keeps the energy infrastructure going. And so the integration of these two things leads a pathway often from the internet through the IT network to the operational network. And so there's a lot of challenges with this merging and a lot of new attacks possible. And so the challenges stem from operational technology, the power grid. It generally, is quite static. Equipment isn't changed out for decades. IT equipment is changed out very regularly. There's a different culture to IT, information technology, and OT, operational technology. And that makes it challenging when you merge the two. So what we're essentially doing is, now that they're merging, we need to harness what's good about them. So you have all of this big data coming at you with the merging of the IT and the OT. And data analytics is key. And we hear a lot about artificial intelligence. And so we're looking at all of the rich information that we have from the IT system as well as the OT system, and essentially creating a data analytics platform that intelligently has situational awareness that could very rapidly make recommendations when there's an infiltration and make recommendations to an operator as to how to react. So we have data acquisition, transformation, storage, and processing in this environment that we're looking at. And so in particular, we're looking at a few things. Currently, we're working on fast intrusion detection and alerting, efficient ways to mitigate an attack. So what do we do? So you're under an attack. The data analytics platform needs to give the human operator some advice on what to do. Like, do this action, open this breaker, isolate this part of the network. This is where the source of the attack. That information should be available. And enhanced incident response as well. And so this is there's several projects with them. This is a multi-year project where we're looking at creating co-simulation, artificial intelligence paradigms, as well as coupling that with real test beds in order to create a data-rich environment where we have this very adaptive system that helps support a human operator. Okay, and the idea here is ideally in this rich environment, even with that connectivity between the IT and the OT, you can prevent attacks from occurring. Okay, so I talked a little bit about, gave a little bit of a flavor of securing the grid, but these principles are very general, so we're also looking at applying them to autonomous transportation systems. Eventually we'll look at medical applications, we're looking at distributed robotics and industrial control systems, and that will lead us ideally to a secure smart city. Thank you very much.
I had trouble trying to figure out the equations for Fourier transforms when I worked in the field. Those other ones you have. Yeah. Anyways, amazing presentation. I should mention that in the summer of '64, I worked for Ontario Hydro at the control center for the James Bay watershed stations in Falconbridge outside Sudbury. There was a security threat, it turns out, that I addressed. The engineer, who was sort of in charge of changing circuits and so on in the center, he'd pull out a circuit diagram. He'd scratch out the change and enter it. And then he threw it under a table. My job was to go under 3 tables and file with things so you could actually find out what the circuit diagrams were. So hopefully you're working on the base of circuit diagrams that are
yeah.
Also, I had walked around inside one of the generators at LG2 in Quebec.
Oh,
that was a few days before René Lévesque turned on the water. Anyways, interesting to see how you're working with these people. I'm going to open this for questions.
So my life is already at risk. I have sleep apnea. I use an Australian CPAP machine, which every morning gives me a log of what it did. But the Australian, the bad actor who decides to get me, can dial right into my machine and change the settings and kill me. So I'm right there. So that leads to the question. We are moving like lemmings to the cloud. So when you talk about checking the source code, and somebody in IT decides to run it on the cloud, it doesn't run that way anymore. And you have no idea how it runs. So the question is, what research has been done or should be done to decide how to isolate these systems, like control power systems, from the more vulnerable areas?
No, this is a really good question. We had actually a project with London Hydro, and so in London, Ontario. And London Hydro is actually a very innovative utility. The cloud is primarily, so people are being very careful of the cloud. London Hydro was one that embraced the cloud, but there are several kinds of processing and networks in the power grid infrastructure. The cloud is typically being used for that related to consumers, business, metering. So for example, there's a standard called the green button standard. It's in Ontario. I think they use it in parts of the US as well. And so the cloud is actually very useful if you're looking at consumer-centric applications, but not so much operations. Okay? Operations is something, it's a highly regulated industry. You would not put the operational technology environment on a cloud. I don't think most energy utilities would even dream of that. What's moving to the cloud is more the usage, the billing, the services sort of thing. So in terms of research, what that would mean is, but you do have a convergence. The last theme I presented, the IT and the OT convergence. So you have parts of the grid that are connected to the cloud, also connecting to the operational technology. So what you really need to do, I mean, it's a very complicated problem where you need to have governance, research, standards, all essentially align. And you would have standards standards give people a process, but they're not too prescriptive, and they can't be, because different utilities have vastly different kinds of system architectures. So what you really need to do is look at it as a process. Be very careful at the interfaces when you join networks together. Have protections in place. And essentially just have a great deal of monitoring. And that's the last theme is what we're looking at. If you have a great deal of situational awareness, and you can correlate different events in different parts, you can likely be able to identify an intrusion if it occurs. So what can you do? It's a process. Okay? And you basically get everybody aligned on board. Yeah.
So we have 3 questions from folks that are live streaming in. I'm just going to ask the first one and hand the mic back. Anon is asking, can an SIEM tool efficiently monitor and detect the attack in a smart grid? If not, what is the way to identify the real-time attacks?
Okay. So I'm unfamiliar with the SIEM tool. But how do we, I can answer the second part, how do we monitor real-time attacks? It's in the last, the third theme, the ITOT convergence, it has advanced monitoring. So having what we call situational awareness, a dynamic operating depiction of the grid, understanding what's happening in the business network simultaneously, what's happening in the operational technology network, having that knowledge, comparing it to what normal healthy behaviors look like, we call it anomaly detection, intrusion detection. Those strategies typically are the best way. First, detect something and then try to react to it. But it's difficult because if you saw in one of the earlier slides, I talked about how they're very stealthy. So what we're moving towards is artificial intelligence paradigms, machine learning that tend to be more intelligent and try to identify these very subtle variations due to stealthy attacks.
I have more, but I don't want to overtake either.
Anyone else? Questions?
Then we have Michael. He is asking, sorry, he just let me know as well that he's a consultant in India. It says here, I'd be interested to know whether there is an overarching governance body in place that looks to ensure unified cybersecurity across various local, regional, national, and international grids. And thank you for a great presentation.
On one of the earlier slides, I talked about the North American Electric Reliability Corporation. So they have been mandated, that's NERC, by FERC in the US, which is the federal authority, to do spot checks, for various utilities in order to essentially make sure utilities are operating according to what I mentioned was the critical infrastructure protection standards. So definitely, this is a highly regulated situation. It's a critical infrastructure. There are bodies, but they tend to be focused. There's international bodies. They don't mandate, but they help, in terms of disseminating information and best practices. But in terms of mandating cybersecurity be used, it's done typically on a national level or in North America on a somewhat continental level.
Yeah, let's way back. Somebody's bringing you a microphone.
That's okay, I can. Are the attacks, can they be determined to be from outside or from inside?
So this is a good question. Attacks can be both outside and inside. The reason is that high communication connectivity makes remote access now possible. You do typically, when you look at securing a system, look at what we call insider attacks. Example would be a disgruntled employee. or an outsider attack. And they have different characteristics. What the stealthy attacks that I discussed do, and essentially over the 2 years where they're sitting there before they really attack the system, they're trying to convert themselves from being outsiders to insiders over time. So they try and get, over time, they mimic the behavior and try and gain access to critical systems that an insider would have. So you can tell, it depends how much information you have. If they're stealthy and they're sitting there a while, you will start to realize when an attack occurs because the system will start to be disrupted. And so at that stage, even if it was an outsider, if they've gotten access similar to an insider, but they're critically damaging the system, you would have to do some sort of forensics later on to figure out what may have happened. It may be more difficult to do real time. But if it's an outsider and it's a sloppy attack, they're not being stealthy, they're not investing years to figure out what's going on, you can usually distinguish it. An insider can have much more damage, and even they use credentials that typically an outsider would have to work very hard for to get.
If I may just add one more thing, are we profiling the person, or are we profiling the country of origin?
So you essentially profile the behavior, and you profile the malware, okay? The operation of the malware. So essentially malware attaches itself to one component of the system, okay? And the malware sits there and it tries to see how other entities in the system behave, devices and humans. Okay? The malware, in one example, can, for example, this is like the Ukrainian blackout in 2015. The malware will then communicate back to the source. That's where you can figure out the source. It'll communicate back to the source what's going on. There will be, in some cases, there will be active individuals then communicating back to the malware to have a series of actions occur. Okay? But it's changing. Now you have malware that's more autonomous, that doesn't necessarily need the manual interaction with a human. Okay? So, but there is usually, at the reconnaissance stage, information is being sent back, and that is your opportunity to get a feel for it. Also, we're looking at the cyber world, but there's also you get hints politically. If you look at the target, like looking at the target typically gives you a hint as to, the threat modeling, right? The threat modeling is important because when you look at an asset and you look at who would want to attack this asset, you get a profile.
Any other questions? Way back in the far right corner. Yes, you got your hand up.
Thank you for a great presentation. Just one question, I don't think you covered it. What recovery strategy being considered against residual cyber risk? Okay,
a recovery strategy against residual
risk, the risk that you have done all this risk evaluation, but there is something there that you may not find.
Yeah.
So that's residual.
Okay, so this is something that you have not planned for that occurs, right? This is pretty typical in cyber security because they have, like, for example, zero-day attacks. Like much of the malware I put on, those are all, they're exploiting vulnerabilities that are unknown previously. Often you have not planned for a certain type of attack. So, okay, so in a typical IT system, what you would often do is you would reboot, okay, and you can't do that with the power grid. So what you essentially do is you've got the two elements I mentioned, the cyber and the physical. Okay, you really effectively can coordinate both. When it gets to a extreme situation, an advanced situation, you really have to try to mitigate and reduce the negative impact that's occurring. Okay, so if it's early on, so you start to see the cascading failure begin, you have to use physical means, and this would be, for example, using the power equipment. Okay, you have to use physical means to try to either, and one of the basic things is you isolate components, you detach components of the grid, you break it apart. Okay, so you break it apart physically and electronically. Okay, and you isolate. So when things are propagating, it can only affect a certain component. Now, in terms of how you bring it up, With the grid, this is not a simple thing. You know what it's like when there's a very large-scale blackout, like the 2003 August. You can't bring it back immediately. It has to occur in stages. Okay, and so typically you would, if it was a severe situation, you break it apart. Components of the grid are still operational. The areas where there's a significant blackout, you would have to first mitigate, try and remove the source of the attack, and then bring the system operational, and that takes a while, and it really depends on the size of the area. Okay.
Thank you.
Thank you for your presentation. I have just a quick question regarding the protocols you may use for cybersecurity. So I've heard like NERC is more used in North America or Asia, but what we have seen in Europe is more like IEC, based on IEC 61850.
Yes.
So based on that, I know that they are different, and NERC is like created for that cybersecurity, and that's the main reason of that NERC. So what would you recommend in comparison of those two protocols they use for digital substations?
Yeah. So they're not equivalent. Okay. So the SIP requirements, those are not prescriptive. They just give general guidelines to a utility. For example, there was different SIP standards. The first standard has to do with identification of critical cyber assets, right? So the SIP standards give you a framework in which to operate the utility, but how, for example, you would prescriptively do what is suggested is up to the utility. And so the 6180, like this 850 protocol you're talking about for digital substations, that is an actual implementation of a protocol. So what you would do, and there's many, with Hydro-Quebec, that's part of our studies with our data analytics platform. You would essentially look at the spirit of the SIP standards, implementing that in 61850, and there's a lot of work in terms of protocols to cyber secure that communication, the substation communication protocol. So they're not competing. Okay, you could borrow from the spirit of the SIP to look at making a secure utilization of the 61850 protocol. Does that make sense? Yeah.
I think Sarah has another question.
Hello, and this is from Lynn Couillard in Southern California. She works for ARM Limited, and she's just saying, interesting on the breach data. On slide 17, 76% of energy utilities had been breached in the past year. What is the source of this data? I have to get back. It was I forget which magazine. It's one of these trade magazines. And I want to mention about the 76%. A lot of the breaches have very low impact. Okay, so the IT department, if they're doing their job, they'll block it early on. Okay.
The only comment I want to make right now is it is very clear to everybody that putting down the power grid is high on the strategy of not the bad actors, but the national state actors.
Yeah.
And that's where a lot of effort is going. Those numbers are less material than what could be done when somebody wants to do something and has the capability.
Yeah. That's a good point. When you get into critical infrastructure of any kind, your threats can be nation states. If you look at if you look at the analysis of the malware that I had on, for example, Stuxnet, it becomes very clear, if you look at how the malware is built, that hundreds of people were likely involved. And even the styles, and there's different, I mean, some parts are clearly experts were working on, other parts, you know, someone, you know, Googled something on the internet, it's very, no, so, but there's, if you look at a piece of malware, it's very complex. It's very clear you have different people with different capabilities simultaneously working on it to build it. It's quite, yeah, it's from an engineering perspective, not from an impact, quite beautiful.
Over here, is there a single country that's the acknowledged leader in this area?
Okay. So in terms of cybersecurity of critical infrastructure, okay. So in general, the culture is that you will not tout yourself as being secure and a leader, because then you automatically become a challenge and a target. So typically, I mean, it's, for example, Jim talked about CAMH, because his son and I collaborate on a project, and I've talked to their IT department. They're always interested to talk to cybersecurity people. They will never talk about the security of their system, because they just don't want to bring it up. But what I have observed, is that the more innovative utilities, like I work with Hydro-Quebec, because they have a fantastic research center and they're open to innovation. And so they tend to, having that research center, that interface to the utility tends to provide opportunities. But also what I've noticed globally, those countries that tend to be targets, maybe I can say, so South Korea is very secure. Okay, so we work, there's South Korean utilities, they're very much, they're very well educated. So often when you have a country and there's a definite need to be secure, they are very much on the ball in terms of security issues. Okay, so when the need is there, and the resources are available, you will see more focus on this.
So, one of the questions I have, having followed this scene for years, I started out as head of the Canadian Alliance Against Software Theft, and we thought that was a security breach. Anyways, but one of the real challenges is not only power operating companies, but even other large organizations to get the C-level executives to realize the importance of security issues. And do you get out and address this at time to time?
Yeah, this is a really good point. So this area has been a focus since I would say about 2009, 10 years. Okay? Initially in that 10-year period, there was some difficulty, especially getting power engineers to recognize from the IT engineers that cyber threats were a problem and that their normal techniques to deal with natural disturbances and faults were insufficient. Okay? So, cybersecurity in the past, not so much anymore, has been a challenge even to discuss to the C-suite. And so essentially, this has changed now. I mean, now people are realizing it's a very necessary part of it. It's not, cybersecurity technology is not a revenue generating thing, so it doesn't receive attention from that perspective. It's not a new bell and whistle, but it's a necessary part of the trust that's needed to use a system. So the culture is changing. Typically, what you often do is, and even cybersecurity consultants, you do have to speak to members of the C-suite, and you typically try to communicate what's going on. I think what you try to do is you think about, how would I speak to a 5-year-old about cybersecurity issues, because it's so technical in your head, and like, how do you make it so intuitive that a child will understand, and essentially that helps you understand how to explain it to non-technical individuals. And that's the general principle that we use in the industry.
Okay, I think with this, I want to say, first off, huge interest in this topic. We've got a big crowd today. Fortunately, we could move into this dining room and take in all who wanted to attend. The amazing part of the day, too, is we now have a technology that we probably have somewhere around, 100 people, Sarah, online around the world.
I have one more, but it's okay. I've let them know that we've gone so far.
And how many people are online, do you know?
Yeah, in total we had 88 people.
88.
And at the moment people are signing off just because they have to get back to work.
But it's just to me, you know, just one more example of where our technology has gone and allows us to propagate this information. And not only that, afterwards, I happen to know of a few friends who are going to get a link to the videos. So, Deepa, this is absolutely amazing presentation. You've taken on a very powerful challenge, and I thank you for your presentation. I should mention, I want to make one more acknowledgement. Just about a year ago, I got an email from Deepa's communications manager asking me if I would let my name stand for an engineering alumni award. I think this is the instigator.
Oh,
Thank
I'll
you.
never tell.
It was an amazing experience, amazing event, and even watching award ceremonies these days, you have a whole different perspective on what goes on. Thanks again for your presentation. Are you around for a few minutes?
Mhm. Yeah.
So Deepa will stay around for a few minutes. I know she has to get back around 1:30, 1:45, but she's around for a few minutes if you have questions.
Great.